see. In section 12.1, number 108. Oh, yeah. So, guys, let me ask you this question real quick. What's the domain of that? What's the domain?
Cannot equals 4.
Yeah, x cannot be 4, or negative infinity up to 4, 4 to infinity. So what's the domain of this?
X cannot be equal to 4.
I like some of these reactions. Good, it's perfect. What's the domain? What's the domain of that? What's the only x that'll freak it out? 4. So does adding 3 do a damn thing to it? No. I love it, because there's nothing wrong with I can add 3 to whatever I want to. The only part of this equation, the only part of this function that has any problems is this guy. He's got a bottom. The bottom can't be 0. It's the same damn answer. So what's it got to do with it? Well, number 108 looks like this. It says to find the domain of this. I like it. So this one, the reason that the domain of this was not 4 was because the bottom cannot be 0. And then if you solve that, you get x can't be 4. Over there, what cannot happen?
Negative.
Yeah, what can't be negative?
The inside.
The inside. So the inside can't be negative. Another way to say that is the inside has to be at least 0. Does that 2 plus do any damn thing to it? No. I can add 2 to whatever I want to. The only problem is in there. I don't want to become complex yet. I want to become imaginary. I want to be real. Right? Real talk, kids. So then you just solve that and you get the domain.
This also says the estimated range.
Oh, well, here you can get the exact range. Range always seems like it's going to be a lot harder. Some functions you have to do it in the calculator to see what the range is going to be. But can anybody tell me what's the smallest that a square root can be?
0.
What's the smallest a square root can be? 0, right? So what's the smallest this function can be? 2. So the smallest output is 2. What's the biggest output? Infinity. You could keep plugging bigger and bigger x's in. Won't that piece get bigger and bigger? So see, you don't need the calculator to figure out the range. You just know what's the smallest it could be and what's the biggest it could be. That's the range.
And the smallest it can be is 2 because of the 2?
Because of the 2, yeah. The smallest this piece of it can be is 0. So the smallest that g can be is 2 plus 0. Can you guys draw for me in the air what a square root function looks like? Who remembers this? That was quick. Careful. That's a parabola. So it looks like a parabola that's done what? Fallen over, and then that part went away. So it looks like that from your perspective, right? So remember, a square root looks like that. So normally the smallest that a square root by itself could be is going to be 0 because it's going to go up from there. Well, this function would just be 2 added, so it would start at 2 and go like that. It just moves it up by 2, what it normally does. So tell me this. There was another question coming up here in a minute. All right, so let's get some of this stuff out of the way. If I asked you, let me start with this. Does it look like this could be modeled using a quadratic function? What would a quadratic function look like when you graphed it? What is a quadratic function? What's a quadratic function? When do you use quadratic formula when you have one? Oh, guys, you can do it. Quadratic. The reason we call it quadratic, it's kind of weird. What's quad mean? 4. And what shape has 4 sides? Square. So a quadratic function would be x squared plus x plus 2, for example. You guys kind of with me? So would this be modeled using a quadratic function? What does a quadratic look like when I graph it? X squared plus x plus 2? What would it look like? What would it look like? X squared plus x plus 2. What would it look like? No, what's happening? So, all right, let's back up a second. That looks like a line. straight line, right? Because it's only got a first power in it. The minute that you have a variable that's to any other power, except 0. So if I have this, so that's going to be a straight line. This is going to be, of course, you guys know this, parabola. It's going to be parabolic. So does this look parabolic is really what it's asking.
Yes.
Yes. So if it says, could this data be modeled using a quadratic? Holy shit. What they're really saying is, does that data look like a U? Right. Now, if I say the same question, could this data be modeled using a square root, a radical function, and I got points like this, could that be modeled using a radical function, using a root? Yes, because that's exactly the shape of a square root, for example, or a fourth root. But could that be modeled using a radical function? Could it? Of course not. It's a freaking parabola. It doesn't have the right shape. So that kind of question shows up. Somebody asked me a question about that. Whoever. Yeah, it's number. I forget. 108 or 116. Yeah, 116. The one about the firefighters. So if you just plot those points, you can see, does it follow? Let's, from my perspective, does it follow a radical form like that up there? I don't know what's doing there. That might be me from some previous. I like that. It's fun. Does that make sense? I mean, there's a whole branch of mathematics which is all about, we go out and we look at the temperature. The temperature goes like that. And we say, oh, maybe that's half of a parabola. Maybe I could use a parabola to model the temperature so I can predict what it's going to be. And, of course, the temperature is going to do what? Go back down, thank God. Right? Just doesn't keep going up. It goes up and down and up and down. It looks like more trig stuff that you'll learn in pre-calculus. It looks like a sine wave. Maybe you guys have heard of that. Right? But there's a whole idea of what kind of equation could I try to write that models my observations, what I see. So if I take track of the temperature, or if I take track of the waves out of Scripps Pier, to watch the waves, and I say what kind of model, what kind of equation can I use to model it so I can predict what the waves will be 3 weeks from now when I've got time to surf, right? So you can look it up online. All right. Blah, 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 blah. So that was 12.1, number 116 there at the end. Let's see. 12.2, I got a question on number 96. Oh, this one's a little bit weird, but they tell you what to do in the instructions. What's another way to say rational exponents? Using a rational, the instructions say use rational exponents to simplify. What does the word rational refer to? What kind of number? Rational. Fraction, because the root word of that is ratio, right? So rational means fractional.
T 6 over 10.
Yeah, so you can rewrite this t to the 6 over 10, which you can reduce to be
2 over 5.
who? 3 over 5. Good. Which you can rewrite back again as
5.
fifth root of t cubed. So you guys see a shortcut now. Just divide both of these by the same number just because it would become a fraction. And you can reduce it that way. Is that cool? Whoever asked that question? Okay. There are 2 people actually, I think, that wanted that one. No, that's me. And just to remind you guys about 12.2 homework, remember there was that typo?
Yeah, 120.
It said 78, no, through 102.
Oh.
Yeah, so you just went a little too far. So that answers those 2 questions really easy. So don't do them. And then 12.2, number 110.
Yeah.
Oh! Sorry. You're the only person in the room I think I would get excited about. Problem. We did this kind of problem before. We can do a problem like this, like 110.
Or just multiply 5 times 3.
Yeah, that's a shortcut. Why does that work that way? Because I can rewrite a cube root of x as... What can I rewrite a cube root of x as?
1/3.
1/3, right? And what do I rewrite this fifth root of this? It would be this to the 1/5, good, because the fifth root can always be written as a 1/5 power. What would you do with the powers? Multiply. So I love it. Then you notice the shortcut is just multiply those two numbers to get the 15th root. Cut it in 5 pieces. Cut those in 3 pieces. How many pieces you got now? 15. Right? Maybe, because that's what a root does. It cuts things into parts.
So the answer is 115?
Yeah, either x to the 115th or the 15th root of x. They're both the same, but it depends on if they ask you. In this one, they didn't say... No, in this one it says do not use fractional exponents. So you have to come back to the 15th root of x. Cool. And then 125... All right. Let's see. This is still section 12, too. 125 gives you this formula.
Okay. Oh, that's...
So k times 2 to the x over 12. Oh yeah. So whenever you get a problem, this is not what I would call a word problem. It's a problem with a lot of words.
Just like
The reason it's not officially a word problem is, do you have to come up with your own equation? No, they gave it. All right. So now this problem becomes a what are the important numbers and where do they go problem.
Order of operation.
Right. This is the easy level problem. This is just plug the numbers in. They tell you that this f represents the frequency of a musical note that is x half steps above a note with frequency k. So x is the number of half steps above frequency k. So the problem says the frequency of concert A for a trumpet is 440 cycles per second. So how many musicians do I have in the house right now? Anybody? All right, so 440 hertz. Yeah, you got little tuning forks, and then you got like one with a little 440 on it. You can bang it, right? So 440.
That's okay.
Good. Find the frequency of the A that is 2 octaves, 24 half steps. So I want to find 24 half steps above 440. So x is the number of half steps above frequency k. So this one little thing tells me 2 things. Like you said, what's k going to be? 440. And I want 20, so x is going to be 24. So k is 440, x is 24. Plug it in. Check it out.
Order of operations.
Order operations.
That's what kept getting.
Dude. So when you put it in the calculator, if you put 440 times 2 to the 24 divided by 12, you are not going to get the right answer. Why not?
No
You gotta
break.
do the exponent first.
What does this do? This does 2 to the 24th, and then it divides that by 12. I'm not supposed to do that. I'm supposed to do 2 to the... So you can just make that 2 in the first place, and then you don't have to worry about parentheses, right? So if you can simplify by hand anything in an equation, do it, because then you'll make fewer calculator input mistakes. How are we doing there? Yes?
For 110, where did you get the Q?
Oh, I did like 110,
Oh,
because now I want you to do 110.
okay.
Because I didn't assign a lot of those, I want you to get a little practice with those. Right. Okay. Let's see. All right, and then 12.3, number 88 is exactly like what we just did. 12.3, number 88, they give you a formula for the braking distance. Any guys ever seen My Cousin Vinny, the movie? If you look at the picture on page 747, number 88, it looks like the picture they used in that movie, but I won't. Cause attraction. So they give you a function where L is the skid mark. This is number 88 and 12.3. They tell me R of L is 2 square root of 5L. This is the length of the skid mark. And R is the speed. So the longer the skid is from your car, the faster you were going, that kind of makes sense, right? Okay, cool. So, and then they ask you, well, how fast was the car moving if the skid mark is 20 feet long, if it's 70 feet long?
Like a,
Yeah, so if I say part A, I want 20 feet long, skid mark on the road, where do I put 20?
I know.
Where do I put 20?
I'll speak to it.
Where do I put 20?
In the L.
In L, because L is the length of the skid mark, right? So those two problems are all about what do the variables represent so I can put the numbers in the right place.
What did it want us to estimate them to? Was it to the...
10. Rounded to 10.
What did it say? Blah, blah, blah. Did it say that? I don't see it.
Rounded to something.
Oh, to the nearest 10th mile per hour. Yeah, because of course when you take square roots, you're going to get something that never ends.
So that would be only like 10, 20, 30, 40?
No, the 10th.
Oh, yeah.
Yeah.
So
So tens, ones, tenths, hundreds, thousands. Yeah. Remember that. Because our number system is based on 10, it goes down by a factor of 10 every time I take a step. Yeah, so round it to the first decimal place. They could have said that instead.
I think the first one is just going to get a nice number without rounding to it.
Could be. Yeah. When you plug a 20 in and get 100 in there, that's awesome. And then you can take the square root of it. But normally square roots of some other number, you're going to get something that never ends. What do you call a square root of 2, for example? What kind of number is that? Some of you know? So, technically, not just what you call it yourself. I got a few names for it. The Greeks didn't think it existed. They didn't trust it. No. What kind of number? We said this earlier. What kind of number is this? It's a fraction, so it's a rational number. So square root of 2 is the opposite of that. It's an irrational number. There you go. Anything I cannot write as a fraction. And a decimal that doesn't have a pattern and never ends cannot be written as a fraction. Because if I can write something as a fraction, that means I have a way to write it as a decimal. You guys with me? Any fraction you can imagine, I can write it as a decimal. You guys kind of with me? One that has a pattern or that stops. So for example, an easy one would be 2 over 10 is 0.2. 2 over 9 is 0.222 forever. And so forth. That's enough of that stuff. They're all fun at tangents. But yeah, square root of 2 is called irrational number. That's why they're going to want you to round it, otherwise you'll never stop writing the answer. Because it goes forever. So these are rational. Okay. So I think that's all the questions. Break. Not break yet. Yes. Oh, yeah. We haven't made it to 12.5 yet, and we actually haven't finished 12.4 yet. So if your question is about rationalization,
Yeah.
there you go. See, we haven't gotten there yet. Okay, let's do it.
Denominator.
So that was the other question down here. All right. So before I get into that, just help me remind me. How would I do something like before we get too far away from this? How do I do that?
Just factor it in
What's a good way to factor that?
3.
49 times 2.
Yeah. So what's going to be 49 times 2, right? Why is that a good way to do it? Because 49.
7 squared.
Yes, square root of 49 is 7. What's the square root of 2? I don't know. All right, cool. That's how you simplify a radical. Now, let's take this another step. What's the square root of 5 times the square root of 5, for example? Careful.
25.
Okay, which is?
5.
And so you should start to realize you can skip the middle step. This is the square root of 25. But think about it. What does square root of 5 mean? 5 to the 1 half. Okay. So a square root of 5 is half of a 5, multiplicatively. So if you multiply it by another half of 5, you should get a whole 5. Aw. So square root of 5 times square root of 5 is 5. Bam! It is square root of 25, but that damn thing is 5. So what's the square root of 11.96 times the square root of 11.96? Holy shit. 11.96. Right? Don't let that freak you out. So What about this? What's the cube root of x times the cube root of x squared?
X to the third.
Cube root of x to the third, which is
X.
x. So 1/3 of an x times the other 2/3 of an x makes a whole x. Oh, neat. Right? You guys start to see what I'm talking about. If a root breaks things down, when I multiply the parts back together, they got to become the whole thing. So I'm breaking x down. When I multiply the parts together, it becomes a whole x. This is x to the
1/3.
1/3. This is x to the
2/3.
2/3. What do you do with the powers?
And
1/3 plus 2/3 is 1. So you get a whole x. It only makes sense if you let it. Radicals are parts of things. When you multiply them back together, you start to get closer to the whole thing again. You're putting all the parts back together. Now trust me, this actually is everything to do with rationalizing the denominator. Right? Because here's the idea behind rationalizing. Now this is not the psychological definition of rationalizing. So for example, what you got, Jeff? Let's do the cube root of, let's just start with something nice. Cube root of 8. So here's the idea behind rationalization. And to be honest, it's actually going to make a little more sense when we get to complex numbers. And a little something we're going to do today also, when I have more terms on the bottom, it gets a little more disgusting. But watch how nice this idea is. I don't call it rationalizing the denominator. I actually call it completing the root. So the one basic idea is roots are bad enough already. They really, really suck when they're on the bottom. Now you could also rationalize the numerator. With some of you guys going on to calculus, you're going to do that a decent amount. So you're getting a little preview of that. Let's focus on the denominator right now. And like I said earlier, what kind of number would this probably be? Cube root of 7. What kind of number is that again?
Irrational.
Irrational. So why do we call it rationalizing it? We're trying to make it rational. We're trying to make it not radical. Trying to kill the radical. Man, some of you guys are already tuned out. Shit. It's not like I can hold you, but you had a quiz. Your brain's already kind of fried. Yeah.
multiply by 1, right?
No.
Multiply
Well,
there.
the only thing you do to a fraction is multiply by 1. But specifically, why can I not do the cube root of a? Because there's only 1a. So how many more a's is it?
Multiply by cube root of a squared. On
Beautiful.
top and bottom.
Multiply top and bottom by cube root of a squared. Now why do we do that? Because I gave the root what it needs. So that it can do it what it wants, so that it's gone. So we're killing it in a nicer way than normal. We're not killing it, we're actually just do your job and go away. Right? Go home. So if I multiply this by the cube root of a squared, why do I do it both? Because I have to. The bottom needs it, the top gets it, I don't care what the top wants. I'm focusing on the bottom.
Why is it by a squared?
Make it a-
Because in order to be able to do the cube root, how many things do I need on the inside? 3. I currently have 1a, so I need... So see why I call it completing the root. You look at the root, and you give whatever it needs until it has enough to do. So I'm going to get on the top, I'm going to get...
To prove that.
That's crazy. And on the bottom, I'm going to get a. Kick ass. I will get the cube root of a cubed, which is a. So if the problem says rationalize the denominator, I know I'm done when the bottom has no radicals. Hopefully I did that legally, but that's how I know I'm done. Alright, this is an easy example. Let's do a little more interesting example. Alright. No more A's. Sure, I like it. Gross. Gross. So this would say the same thing. It says rationalize the denominator. So now you know how to look at this. If you realize again what that means, you know how to look at it. What does it already have in it? Does it need 4 more 8s? What's a better way to do it? What's 8 already?
2.
Yeah, it's 2 times 2 times 2. So how many more 2s do I need?
2 more.
2 more because it needs 5 total. Don't let this be more difficult. That's it.
4.
Right? So it needs... Where'd you go? There you are. So it needs the fifth root of 2 squared, or 4, whatever you want to write it as. Why did I put that there? Because it has 3 2's. It needs 2 more to make 5. How many more m's does it need? 1 more m, because it's already got 4. The minute I do this, what I have to do on the top, same damn thing. So what do I get on the top? Yeah, they're both the fifth root, so I just slam them together. So the top just has, whatever the hell happened, just happens to them. The bottom, we specifically did it so that what comes out? 2m. Because, let me do this, let me show you one more step there you should need. This will be 2 to the 5th, m to the 5th. What does the fifth root do with the fifth powers? Kills them. It does its job, so it can go. So on the bottom, I just end up with 2m. That 5 was free. Can I cancel the 2 into the 4?
No.
Why not? Because it doesn't have a fifth root on it. You can only divide or multiply if it has the same root. So don't take these problems too far. You guys with me on that? Let that be easy. I feel comfortable saying that. Even if you don't quite understand it, don't feel bad. You're looking at it a little bit wrong. It shouldn't be that difficult. If it was a 7th root, I would have needed 4 more 2's and 3 more m's. That's it. That's it. And if I asked you the same problem, but I said rationalize the numerator, what would you have done instead? Multiply by fifth root of y to the 4th, because it needs 4 more y's. So whichever one they reference you to do, it's the same thought process. You just give it what it's missing. Be with me. Go with me. Alright, so right at this moment, you don't fully understand why the hell that's so important. But at the end of the semester, you will. And especially in your next class, and especially if you get to calculus, holy shit. There'll be a few things you couldn't do at all without this idea. Okay. Okay, so that's that. Any questions on rationalization? You got to try them out. Yes?
I have a question on number 87 in 12.4.
Oh, okay. I like it. This is awesome. Let me kind of get you into my mindset. Yes. Why not? This bar means division, and I am subtractor. So you're being optimistic, which is good normally. If there's a times in the middle, all day long, you just kill those two, right? I'm glad you brought that up because I forgot that's a huge common mistake. I can't cancel it. Not the right operation in the middle. But when I see this, I don't even see the radical. I don't see I see a whole number minus a fraction. And how do you do that? Common denominator. Common denominator.
Square root minus 3.
Say again?
Square root of 4.
Yes. So what am I going to have to do with this guy? What's currently on his bottom? 1. So I'm going to have to multiply top and bottom by?
A squared. So then it just becomes a squared minus 3.
Good. Root a squared minus 3 times root a squared minus 3 is a squared minus 3. Right? A square root of something times square root of something is something. You guys believe me? Because I would get square root of a squared minus 3 squared, and don't those just cancel, right? Right. Okay. Over square root of a squared minus 3 minus a squared over, so I can go ahead and combine them now because they have an LCD. So then on top I get a squared minus 3 minus a squared. So what happens there? A squared cancels and I get negative 3 over that. which you could rationalize, but they don't really ask you to, so you can stop there. What would I multiply top and bottom by to rationalize this? If I needed to rationalize this. What does this have inside of it? Don't overthink it. What does it have inside of it? It has a squared minus 3. It has one a squared minus 3, so you need another a squared minus 3. I don't look at it as it needs one more a and two more 3's because it's a minus in the middle. This is a single term now, right? A squared minus 3 is one thing. I only have one of them. I need one more. But it didn't say to, so you can just stop here. That's fine. Maybe stop there for a second. So that problem, they actually have it kind of like in a bonus little section, but it wasn't really that hard, truly, because math doesn't care what's there. It just says, oh, you got fractions and stuff, you need LCD. But I got a square, you need LCD. I don't care. Right? He's got a 1, he needs that, give it to him. So a lot of the trouble students have with math is you think that a problem looks different, so there must be a different way to do it. No. This is basically fractions, subtracting fractions. I don't have LCD, I got to make an LCD. Then it becomes a little bit easier to look at when you realize you worry about what form is this in, what's it really asking me to do. How do I do that? LCD. But again, this is a little bit of a bonus. I don't know if you've noticed, but if I give you anything past the word synthesis in the book, synthesis, they're normally like bonus questions, like a little bit harder than normal. So those are the only ones you're having trouble with. You're doing really good. All right, anything else from 12.4? All right, what do you think? Now's a good time to take a break?
Yeah.
All right, come back at 5 after.